Hey, thank you all for tuning in for my talk this morning. Today I'm going to be talking about mixed mode seismic and aseismic slip of an active low angle normal fault in Papua New Guinea. And before we get started, I just want to thank all of my collaborators, including those at UT, Laura Wallace, Luke Lavier, Fred Taylor, Danny Stockley, and Ann Chen, along with everyone else listed up here, as well as many, many people in Oro and Milne Bay provinces in Papua New Guinea. Today we're going to be talking about low angle normal faults. So what's so special about a low angle normal fault? Well, a low angle normal fault is one that dips less than about 30 degrees to the surface of the Earth. So in a general extensional tectonic regime, we expect that sigma 1, the maximum principal stress, will be vertical, and faults will form at about 30 degrees to that stress, which means a surface dip of about 60 degrees, as you can see in the figure over here. However, we see abundant geologic evidence of kilometer scale offsets on low angle normal fault structures that dip less than 30 degrees. And so there's been a long-standing debate about the mechanics of these faults, including questions of how they're able to slip mechanically, and also whether they slip seismically or aseismically. So some of the possible mechanisms that have been proposed for allowing slip on these low angle structures include rotated principal stresses, high pore fluid pressures, or really frictionally weak fault zone materials like clay-rich gouges. Inactive examples of low angle normal faults are common, but active ones are quite rare and slip very slowly. So why are these structures so important? They are really integral in exhuming metamorphic core complexes, which are some of our deepest exposures of crustal material at the surface of the Earth. And these serve as windows into the pressure, temperature, and mineralogical conditions at different depths in the mid-crust. As you can see from the diagram here, these domal structures are exhumed along low-angle normal faults, as shown down here. And these structures are common between many geologic or tectonic settings, including continental settings and oceanic spreading centers. You have oceanic core complexes as well. And here's a global map of all the core complexes from Whitney et al. So these are really abundant structures. So better understanding the mechanics of how they're exhumed to the surface of the Earth is important. As I mentioned, another important question about these faults is whether or not they slip in earthquakes or creep aseismically. And one of the reasons we don't have a better handle on this question yet is, one, because these faults are really rare, and two, because the active faults, the low angle normal faults, slip very slowly. So this is one of the best documented active low angle normal faults, the Alto Tiberina fault in Italy, which slips at about 2 to 3 millimeters per year. So that's actually 2 to 3 millimeters of horizontal extension per year. GPS data across the fault looks like this profile down here, where velocity is on the y-axis and the distance relative to the fault trace is on the x. So you can see this small step across the fault, and this has been modeled as 2 or 3 millimeters per year of slip, mostly by aseismic creep below a really shallow locking depth. So this data has been interpreted to imply that low angle normal faults are mostly aseismically creeping and should not be able to rupture in large earthquakes. Another reason this is an outstanding question is because there's little evidence for large earthquakes or much seismicity on low angle normal faults. The largest low angle normal fault earthquake that we know of is this event from the north of the Moresby Seamount in the Woodlark Rift of Papua New Guinea, which appears to be located right along this seismologically imaged low angle normal fault structure seen here from ABERS 2001. Over here on the left is just another study's interpretation of the geodetic data from the Alto Tiberina fault, which shows that that data is actually fit equally well by this heterogeneous spatial pattern of fault locking, where the red patches are more strongly locked and the yellow parts are creeping. So one question we can ask is whether there's a faster slipping low angle normal fault that we can look at in order to determine whether these faults are able to be strongly locked or if they're creeping aseismically. And luckily for us, there is a faster slipping low angle normal fault, the Mayu fault in Papua New Guinea. So here we're looking at Papua New Guinea, where the Australian plate makes up much of the Papuan continent. And we're down here in the southeastern Papuan Peninsula. That we have extension along this red fault here, the Owen Stanley fault zone. And extension is being driven by northward subduction of the Woodlark microplate at the New Britain and San Cristobal trenches. And this northward subduction drives seafloor spreading and full rifting in the eastern part of the Woodlark Basin, which is propagating westward into the continental portion of the Papuan Peninsula. And we have continental rifting occurring along the Mayu low-angle normal fault. Here's a zoomed in map from this box right here, which shows the Mayu fault in red over here, which steps offshore and runs along the Goodenough Bay coastline. The Mayu fault, where it crops out at the surface here at the base of the Damon Dome, dips about 16 to 24 degrees to the surface. We have geodetic slip rates estimated up to 1 centimeter per year by Lara Wallace et al. In 2014. Beryllium-10 exposure dating of quartz veins in the lowermost part of the fault scarp that's exhuming the Damon Dome infers a slip rate of 11.7 millimeters per year from Weber et al. 2018. And this is the main structure accommodating an extension on this part of the rift. And it exhumes the Damon suckling core complex, which is one of the youngest and most rapidly exhumed metamorphic core complexes in the world. Here's a photo showing the Damon Dome, so this domal exposure of mid-crustal rocks being exhumed along the Mayu fault, which the trace of which is shown by this label here. So how do we know that this fault is active? Well, first off, it's exhuming the Damon Dome, but also we have geodetic evidence from a GPS study by Lara Wallace et al. In 2014, showing about 1 centimeter per year of extension across the fault. We also have microseismic evidence that the Mayu fault is active. So here's a study by Jeff Abers in 2016, which looked at microseismicity through the southeastern Papua New Guinea region. Here, the microseisms are colored by depth, but what we want to zoom in and focus on here is this profile E to F that goes right through the Mayu fault. So here's the Damon Dome and the Mayu fault. We're going out to the coast, and when we plot that up, well, they plot that up with depth, we see this really nice planar alignment of microseismicity from about 12 to 25 kilometers depth, which is thought to delineate the Mayu fault at depth. And so this microseismicity likely represents small frictional failures within an otherwise creeping fault zone at these depths. So the questions that we want to ask in this project is, first off, what controls the seismic behavior of low-angle normal faults? And our hypothesis here is that the seismic behavior should be dependent on the frictional properties of the fault zone rocks, the pore fluid pressure within the fault, the strain rate at which the fault's being loaded, as well as other tectonic conditions like the geothermal gradient. The second question we want to ask is whether the Mayu fault slips in large earthquakes or creeps aseismically. And our hypothesis here is that based on the geodetic evidence from other low-angle normal faults like the Alto Tiberina, we hypothesize that the Mayu fault primarily creeps aseismically. And in the brittle portion of the crust, we infer that that would be through stable frictional creep. And below the brittle ductile transition, we infer that this would be through dislocation creep. So that's the hypothesis we're going to be testing for that one. Just a quick outline of how the talk is going to go. We're going to start with some theoretical numerical modeling using rate and state friction to get a handle on what controls the seismicity of these faults. We'll then transition into a campaign GPS experiment on the Mayu fault. We'll follow that up with a coral paleogeodetic study from the Goodenough Bay coastline. And finally, we'll take the results of these three parts and combine them with other geologic and lab evidence in order to try to understand the mechanical slip behavior of the fault in 3D. As I mentioned, we want to use numerical models to look at the mechanical conditions that control whether low-angle normal faults slip seismically or creep aseismically. Here we have some seismic reflection data showing a well-imaged low-angle normal fault from the basin and range from Velasco et al. 2010. But how do we translate this image of a low-angle normal fault into a mechanical numerical model of seismic cycle slip behavior? First, let's talk about some of the basic theory underpinning most of the topics we're going to look at today, which is the elastic rebound theory of earthquake faulting. This was developed by Harry Reid after the 1906 San Francisco earthquake, and it's shown here by this fence illustration from the USGS. We start with a feature like a fence line that spans the active fault at some time t0. The fault is then loaded by far-field tectonic plate motion, like the Pacific plate moving relative to the North American plate across the San Andreas. And during the interseismic period, the fault is locked or stuck. So the fence far away from the fault moves with plate motion, while the part right above the fault stays locked in place. This smooth curved line shows that elastic strain is being stored in the crust around the locked fault, which is eventually released during seismic slip in the next earthquake. With some of that stored energy is then released as seismic waves or seismic radiation. So on seismic cycle timescales, the upper crust around the fault behaves as an elastic solid. Elastic strain accumulation around locked faults is really important because it lets us use interseismic surface displacements to infer whether a certain segment of a fault is locked or creeping. So here's an example from the San Andreas fault. And let's first look in at this area here where the fault is red. And we see that the velocities on either side of the fault are pretty much parallel to one another, but facing the opposite direction. So this red profile is another way to look at these velocities. So here we're looking at the fault parallel velocity on the y and the distance to the fault on the x-axis. And this sharp jump in velocities across the fault is indicative of a creeping fault. So there's very little elastic strain being accumulated around this segment of the fault. But on the other hand, we can look down at the Parkfield segment instead, which hosted a relatively large earthquake, and we see that the velocity arrows actually diverge from being parallel to one another across the fault to pointing towards the fault or away from the fault. And so this pattern, which translates up to this blue profile here, this smoothly sloping profile across the fault trace, corresponds to a locked patch of a fault. So this is a locked segment that's storing elastic strain due to fault locking. So in addition to elasticity, another mechanical component that we'll need for seismic cycle models is rate and state friction, which describes the frictional stability of geologic materials as seen from lab experiments. Basically, rate and state friction tells us what happens to the friction of a surface if the slip velocity across it increases. So if the effective frictional strength of the material increases when the slip velocity increases, then its velocity strengthening and tends to slip or creep stably or aseismically. If friction decreases with higher slip velocity, then the material is velocity weakening and potentially unstable. So velocity weakening fault materials are more likely to allow fault locking and seismic slip. And these behaviors are broadly described by the lab-derived parameters A and B, which describe the direct effect and the indirect effect on friction from the velocity step. And lab experiments for different rock types typically show low temperature velocity strengthening behavior, followed by higher temperature velocity weakening behavior, and transitioning back to velocity strengthening behavior above temperatures of 350 to 400 degrees C. And we can quickly look at how these map with depth in subduction megathrusts or crustal faults. And we see that rate state friction stability outlines the seismogenic regions of these faults pretty clearly, where the pink region here is the potentially unstable region, and over here on the right is the earthquake distributions from these regions. So in the models we're going to look at here, we model the fault as a frictional interface between two elastic bodies. And up here we have the fault geometry as approximated from the seismic images, which we map to the piecewise linear modeled fault down here. And we map rate state properties onto the fault with a small velocity weakening zone down to about 7 kilometers depth. And then we also map effective normal stress with depth based on the lithostatic load of the hanging wall. And then we pull the fault, so we load the fault by pulling at 3 millimeters per year in extension. And after we load the fault, or while we load the fault, we also model the slip velocity based on rate and state friction using the equations from the last slide. So the plots from these models are a little tough to digest at first, but let's just walk through this one. On the x-axis, we have the distance down dip on the fault, and then on the y-axis, we're looking at the cumulative slip on the fault. So each of these contour lines show how much that section of the fault has slipped at a given time. And here, the blue lines are plotted every 20 years when the maximum slip velocity is less than 100 times the plate velocity. The red ones are plotted once per second when the slip velocity is above 1 millimeter per second, which we can think of as the seismic slip velocity cutoff. So the red contours through here show the earthquake slip patterns. And finally, the green patches are the intermediate regime where the velocity hasn't reached seismic velocity, but it is faster than plate rate, or significantly faster than plate rate. So for this model, we have a seismogenic patch about 1 kilometer wide with interseismic creep, up dip, and down dip of it. And now we can look at the slip velocity with time for the point shown by this orange star here. On the y-axis, we have the logarithm of the slip velocity with a green reference line for the plate loading rate of 3 millimeters per year, and the red line as a reference for the seismic velocity cutoff. And we can see that the earthquakes here are almost perfectly periodic, with these really fast, short slip events shown by these spikes being separated by these periods of interseismic locking, where the fault is locked and accumulating elastic strain. Another way that we can look at these results is by looking at the cumulative slip or the cumulative displacement. So here we have cumulative slip on the y-axis and time on the x-axis. And for the pure or periodic seismic cycle case, we have this stair-step pattern where most of the slip is being accrued in the periodic earthquakes. In contrast, we can look at a point down here in the creeping region of the fault zone, and we would get this constant line where the slope reflects the plate loading velocity. So we're interested in how the frictional properties of the fault affect its slip style. So we tested models where we decreased the magnitude of this velocity weakening peak, and we also decreased the width of the velocity weakening region. We're starting here with this red A-B profile that you see here, which led to the periodic earthquake cycles that we looked at in the last slide. So by decreasing the peak of this A-B profile, we start seeing episodic creep events that don't quite reach seismic velocities. And these are these little peaks through here that precede the earthquakes. So each earthquake in this regime has a few creep events before it slips seismically. Then by decreasing the peak of A-B even further, we start seeing a regime where we have clustered earthquake slips. So we have a few earthquakes separated by creep events, and then we have over 1,000 years of these aseismic creep events. Eventually, this transitions to aseismic creep. So if this peak continues to decrease, we eventually end up in the steady creep regime. And then this regime here is the area where we would have periodic creep events with no earthquakes at all. So the main result here is that smaller, less velocity weakening locked zones generate fewer, smaller earthquakes. In these rate and state friction models, we've assigned an A-B value to describe each patch of the fault. But it's worth asking what this bulk effective A-B value really represents in terms of the fault zone properties. So one interpretation is that the bulk A-B value could correspond to the volumetric ratio of the competent velocity weakening class to incompetent velocity strengthening matrix material in a mixed fault zone or shear zone. So fault zones with higher proportions of matrix could creep more easily than fault zones with lots of strong class that jam together and cause the fault to become frictionally locked and start storing elastic strain. So this interpretation is based on work by Fagereng and Simpson down here, who looked at outcrops with different class to matrix ratios and inferred the slip behaviors of based on these outcrop ratios. And then over here on the right, we've plotted how our rate and state normal fault model slip behavior regimes correspond with A-B, and then we've drawn in our interpretation of what the architecture of the fault zone might look like for these different slip behaviors. So down here, we would have more matrix material allowing for steady aseismic creep or these periodic creep events. And in here, as the class start to dominate the shear zone, we get more locking and more seismic slip, eventually leading to this really tightly packed shear zone with mostly class material that could lock up and lead to mostly earthquake slip. Finally, I just want to mention that our results correspond well with rate state friction models from subduction zones, which showed that seismic style depends on the ratio W over H star, where W is the down dip width of the velocity weakening region, and H star is a critical nucleation size. So this ratio, as you can see here, depends on the magnitude of A minus B in the weakening zone and the width of the weakening zone, but it also depends on the effective normal stress, the shear modulus, and Poisson's ratio. And we can see that low W over H star ratios lead to aseismic creep, as shown by this green regime, whereas higher W over H star values lead to seismic cycle slip, which is the black events over here. And then there are these transitional regimes in between where there's periodic aseismic creep or some earthquakes with other periodic creep in between. I mentioned that rate state models usually map A minus B with depth based on some assumed geotherm. And on the left here, we have an example of that from Mark et al. 2018, which shows the temperature on the fault colored in rainbow colors and the A minus B profiles that are mapped to these temperatures shown over here by these red and blue lines. So if we assume some geotherm and temperature dependent rate state friction behavior, then we can apply these to normal faults and ask how normal fault dip affects the seismic stability of the fault. On the left here, we have a 60-degree dipping normal fault, and the down dip width of the velocity weakening region is shown by this black line labeled W here. But as the fault gets shallower, the down dip width of the velocity weakening region increases, meaning that the fault should be less frictionally stable. So assuming a similar geotherm in mineralogy, the rate state friction predictions say that low angle normal faults should actually be more seismogenic than their more steeply dipping counterparts. And down here, we're plotting an example of how W over H star would vary with the dip angle, and the different stability regimes are shown by these dashed black lines. So we'd expect a normal fault dipping 25 degrees to be more seismic than one dipping 60 degrees, which would be more likely to creep. Next, I'd like to talk about our GPS experiment across the Mayu Fault. So seen here on the left are the network of sites that Laura Wallace, Susan Ellis, and I installed in 2015. The light blue, red, and purple sites were newly installed, and the dark blue sites represent those from the Wallace et al. 2014 study. And the Mayu Fault is running along here in red at the base of Mount Damon and the Damon Dome. So when we install these sites, we dig a hole in the ground and fill it with cement. And in that cement, we place a stainless steel pin, and we measure the position of that point at the top of the pin using high precision GPS receivers and antennas like the one shown here. By measuring the position at the surface of the Earth over multiple years, we're able to estimate the velocity at which the surface is moving, and we can use that to infer properties of fault zone deformation on the Mayu Fault. So one of the first order results of our study is a GPS velocity field. So the new sites are the ones down here, this dense collection of purple vectors. The other purple vectors are velocities from the sites in the Wallace et al. 2014 study, some of which were remeasured in 2015, 16, and 18 as well. And you can see that the new velocities are generally in line with rapid counterclockwise rotation of all of these sites in the Woodlark area relative to the fixed Papuan Peninsula and Australian plate. So all the vectors shown here are relative to a fixed Australian plate. Zooming in on the new sites, we can see a coastward increase in strike perpendicular velocity going out from the trace of the fault out towards the coast. So imagine taking a profile through these sites and plotting the velocity, the coastward velocity, or the velocity perpendicular to strike, which is what we see down here. So on the y-axis, strike perpendicular velocity, and on the x, we have the distance going out from the fault trace, which would be right around this site here. So this dot is this site, the MCA. And again, we see that coastward increase in velocities, a profile that looks like this, with the footwall being represented by this site here at 0. So one way that we can model GPS velocities is with crustal elastic block models. So in these models, what we want to do is take regional, kinematic, and tectonic data and use them to constrain models of block rotations. So we parameterize the the motion of the crust as separate crustal blocks, which are all elastic. And so you draw boundaries between these interacting crustal blocks, like shown here in Cascadia. Then, by using regional kinematic data like fault slip vectors, earthquake vectors, and GPS velocities, we invert for the degree of coupling or locking on the faults that bound these blocks, as well as the poles of rotation of those blocks. So by inverting for the poles of rotation, we get the general block motions, and we can then invert for the coupling that occurs on faults that leads to the residual, which is inferred to represent elastic strain along those faults. So the inputs to these inversions are GPS velocities, fault slip vectors, and block geometries and fault geometries. And we invert for poles of rotation, slip deficit rate, and fault kinematic coupling. And this is what leads to images like these, which you might have seen for the Cascadia subduction zone, where they're plotting slip deficit rate. So this is the difference between the predicted rate from block motions and the observed surface velocity from GPS or INSAR. Here, the warm colors show areas with high slip deficit rates, so these are regions inferred to be strongly locked, and the cool colors show low slip deficit rates, where the fault is inferred to be creeping at close to plate rates. For a complex tectonic region like southeastern Papua New Guinea, we have multiple crustal blocks interacting, and Lara's 2014 study showed that this block configuration with a Trobriand block, a Papuan Peninsula block, the Australian plate, a woodlark plate, and then a few blocks in here through the D'Entrecasteaux Islands and Goodenough Bay is the preferred configuration. And we tested a variety of block configurations as well and found that this configuration also fits our GPS data quite well. So here are the results from those inversions for both poles of rotation and fault coupling here. The coupling coefficient, or the degree of coupling, is shown in pink and purple, where pink is more strongly coupled, so that would be fault locking, and purple is less coupled, where we infer that the fault is creeping. You can see that along the Mayu fault near our transect, we have only very shallow locking. So this pink region right along the fault trace extends down to about 2 kilometers depth, at which the result transitions to a creeping fault below that depth. So we infer really shallow locking out of these models. Taking another profile, y to y prime, through these velocities and plotting up, again, velocity on y and distance on x, we can see our data are these black dots, and the inferred surface velocities predicted by our model are shown in green. And this, breaking that down, you can see that this is the combination of this dashed purple line, which is the block rotation component, and the dashed pink line, which represents the elastic component. So the amount of that block rotation component that's not being seen in our surface velocities. Taking that same profile, we can now do 2D planar dislocation models. And the goal for doing these is that we can focus in on how parameters of the Mayu fault, like dip, slip rate, and locking depth, actually affect the fit to the data. So now that we have the reference frame with the footwall fixed reference frame where Australia is fixed, we can project our velocities and do these 2D planar dislocation models, where we assume that the fault is some plane that's locked down to some depth, slipping at some slip rate. And we cycle through dip angles of about 1 to 80 degrees and slip rates of 0 to 20 millimeters per year, and locking depths of 0 to 25 kilometers depth. We can see how the results of these different parameters affect the fit to the data up here. So the more shallowly dipping fault, this yellow one, leads to this more drawn out profile of surface velocities, whereas the more steeply dipping purple fault leads to this profile of velocities. We can get better fits to the data. So here's a locking depth of 2 kilometers, which is similar to what came out of the block models, and a slip rate of 10 millimeters per year dip slip. And again, these are just illustrations of what the model outputs look like, but really we're spanning the parameter space as best we can. And so for any given fault dip, we have a plot that looks like this, where we plot the fit to the data by the reduced chi-squared. So here, warm colors are showing a better fit to the data, and cool colors are showing a worse fit to the data. So for a 26-degree dipping fault, we know that the slip rate is probably around 10 millimeters per year, and the locking depth is somewhere between 1 and 3 kilometers. So going through the best fitting results of these models, first we started with models where the fault is locked to the surface, which is the classic consideration of fault locking, is that the surface is locked no matter what and won't slip until the deeper portions slip. So here with surface locking, the best result is a 26-degree dipping fault, slipping at 10 millimeters per year dip slip, locked down to 2 kilometers depth. And you can see the fit to the horizontal velocities here and the fit to the vertical velocities here. But we also wanted to consider the possibility that there might be a more strongly locked patch at depth than at the surface. So we also performed models where we buried the dislocation. So now we have a locked zone at depth and we have creeping zones up dip and down dip of this locked zone. And we also allow for the creep at the surface to be propagated along these splay faults in the hanging wall. So rather than going directly to the observed fault trace, we now allow it to go outboard of site YMCA because YMCA has mostly the motion of the footwall. And so in these models, we consider it a footwall site. Now we see that the best fitting model dips 35 degrees, has a dip slip rate of 10.5 millimeters per year, and is locked from 5 to 16 kilometers depth. And you can see that the horizontal fit to the data is really good as well. And we get a chi-squared of 0.89, which is slightly lower than the fit to the data for model 1. But these two are very similar. So now we're left with two very similar, two models that fit the data very similarly well. So how do we evaluate them? Well, one way to evaluate them is to go to the field and look for field evidence of the fault slip style. One way that we can look at patterns of fault slip on the Mayu Fault is by looking at patterns of coastal uplift along the southern Goodenough Bay coastline. Here, the Mayu Fault steps offshore and parallels this coastline where we see the fault travel around through these yellow starred regions. And these stars represent uplifted coral platforms. Zooming in on this black box here, we can see the topography of the coastline in relation to the sample locations. And looking along strike, we can see these triangular facets, which are fresh, young dip slopes of the Mayu Fault. Therefore, by tracking the coastal uplift at these stars, we're able to piece together the Holocene slip record of the Mayu Fault through this region. So how does coral paleogeodesy work? The main principle is that corals die when they're emerged above sea level and exposed to the air. When they die, they stop fixing radioactive isotopes into their skeletons, and so we can use those concentrations to date the age of emergence above sea level. They also record uplift by their morphology. So the intertidal zone, shown here in gray, is highly erosive due to the presence of small creatures like echinoids and these creatures that live in the intertidal zone and erode the coral morphology. So if the coastline uplifts gradually, we expect poorly preserved corals, no distinct platforms or terrace levels, and gradually increasing emergence ages. Whereas if the coastline uplifts rapidly, we would expect the corals to preserve their morphology, including the platform morphology on which they grew. We would also expect a notch to form below the platform where the intertidal sea level erodes the flank of this part of the reef, and we expect clustered emergence ages. One way to look at this is through a tidal record. So here the tides fluctuate from about 0.8 to 0.2 meters of tidal height. So the height that you would need to emerge these corals in order for them to escape the erosive intertidal zone is about 0.6 meters, shown over here. So episodic uplift would need to lift the reef up to this level in order for them to preserve their morphology and show clustered emergence ages. So to look at these uplifted corals, Fred, Luke, and I went out in a dinghy and we sampled various outcrops of corals along the Goodenough Bay coastline. The sampling methods are pretty straightforward. The goal is to find intact, pristine coral heads that have really clean interiors. So we're looking for really pure white interiors in order to avoid contamination by terrestrial sedimentation or groundwater. So here's an example in the lower right. You can see the coral head intact, and when you crack it open, there's this pure white interior, meaning that it's a clean sample that will hopefully record the most accurate age of uplift. We also measure their elevation above living coral level, or if living coral is not available, above sea level, which we then correct to living coral level with a tide gauge. These samples are separated and then measured for their uranium thorium series isotopic concentrations using ICP-MS. This is done by Rivershen at NTU. These concentrations give us the ages of emergence, so the ages when these corals died. And these are the minimum ages of emergence. Here are the results from site D. So on the y-axis, we have elevation, where the sample was taken from, and on the x-axis, we have the age as recorded from uranium thorium dating. You can see that the ages are pretty well clustered in time. So we have these individual clusters which yield similar ages, and they're also clustered in terms of elevation. And that's because we sampled them from individual platforms. One way to look at this a little more clearly is to also schematically plot in the substrate morphology or the platform morphology, which you see here in the blue line. So now we're approximating the horizontal distance from the coastline and also plotting that relative to elevation. And so we can see that the corals from similar platforms yield similar ages, which are clustered in both space and time, suggesting that these platforms were uplifted episodically in individual uplift events. So here are some photo examples of these platforms that we're talking about. In the upper photo, you can see this well-defined platform near sea level. Then you see this eroded notch, which is the intertidal sea level notch above it. And then above that, another well-defined platform. Within those notches, we found abundant evidence of echinoid burrows, which shows intense bioturbation and bioerosion. And we can see that in the sea level notch here. And that suggests that this part was exposed to intertidal erosion for a long period of time. All of this together, the clustered uranium thorium ages, the platform notch platform sequences, and the echinoid burrows imply punctuated episodic meter scale uplift events or emergence events. And we mentioned that emergence is evidence of relative sea level fall. So we know that we have episodic relative sea level fall. However, we also know that the regional Papua New Guinea sea level fell less than 1 millimeter per year in the last 6,000 years. And so because we don't see any abrupt sea level fall, we interpret this emergence as episodic tectonic uplift events, which we interpret as earthquakes. So these platforms we interpret as evidence of earthquakes, but how large were the earthquakes, and did they rupture the underlying low angle normal fault, the Mayu fault? Well, the maximum coseismic uplift increments from the coral platforms range from 0.5 meter to 1.8 meters. And the surface dip of the dip slopes that run along this coastline are about 45 degrees. So we think that these are higher angle splay faults that splay off of the low angle Mayu fault. You can see this schematically from Weber et al. 2020, where he's mapped the main splay fault of the Mayu, the Guara fault. So that's this little bit in red, which intersects with the Mayu fault at depth. So the corals that we're talking about are further offshore. So they're along strike over here, where the Mayu fault is modeled to dip 25 to 35 degrees based on surface modeling, which is also based on microseismicity and many strike and dip measurements of the Mayu fault that Sam did. So knowing this, if we take a representative uplift increment of about 1.2 meters, that implies 1.7 meters of slip on a 45-degree dipping normal fault. And using moment slip scaling durations, we can estimate a moment magnitude of about 7.3. And also using length width scaling relationships from Leonard 2010, we can estimate the rupture dimensions for the earthquake that caused this uplift. And we see that we have about 29 kilometers of down dip distance and 67 kilometers of long strike distance. And so although these are rough estimates, the 29 kilometers down dip estimate is large enough that we know that there was significant slip on the low angle Mayu fault, even if the intersection depth of the splay and the Mayu fault were as deep as 3 kilometers. So using all of this, we infer that there was seismic slip on this section of the Mayu fault down to about 15 kilometers depth. Next, we can walk through the Mayu fault rock sequence and see what can be learned from the geology of the fault rocks. So Little et al. 2019 detailed the exhumed fault rock sequence from outcrop. Walking through this, the top yellow section is the hanging wall sedimentary rocks, the Guara conglomerate. Then this red line is the principal displacement surface, which is the sharp contact between the hanging wall material and the rest of the fault rocks. Below that are mafic gouges and also saponitic clay-rich gouges. Below that is an ultracataclysite layer, and below that is the foliated cataclysite brecciated layer. Underneath all of that is the mafic myelinite zone. In the foliated cataclysites, there is evidence of pseudotachylites or glassy earthquake melts, which form when earthquakes slip, melt the rock in the fault zone. And so these are evidence of seismic slip on the Mayu Fault. Argon ages of these are as young as 2.2 million years, and this implies that at a slip rate of 10 millimeters per year, these were formed at 10 to 12 kilometers depth. So we infer seismic slip at these depths on the Mayu Fault. There's also evidence of mutually cross-cutting veins, faults, and folds of foliations that were formed by diffusion creep. So the mutually cross-cutting nature of these implies that there was mixed frictional viscous slip in the fault zone within the foliated cataclysite units at the depths at which they were the actively deforming units. We can take samples of these rocks, and Carolyn Bolton's done this. She took samples of different fault rocks from the Mayu Fault and performed frictional velocity stepping experiments in the lab. So these are similar to the rate state plots that we were looking at earlier. So here on the y-axis is the effective friction coefficient, so the frictional strength, and on the x-axis is displacement. So everywhere where there's a little bump, that's a velocity step being applied, and then the resultant friction is being measured before the next velocity step. So these plots are for the saponite gouges, so the shallowest gouges in the fault zone. And now we can invert for A minus B, the rate state friction stability parameter that we talked about earlier. And we find that for the shallowest saponite gouges, most of the A minus B values are positive, which means that these gouges are velocity strengthening and should promote stable creep. Very few conditions lead to any sort of velocity weakening behavior. So here on the right, we'll walk through a table which shows the fault rock unit, the friction coefficient, and the frictional stability from the velocity stepping experiments. So first up are the saponite gouges, which are frictionally weak, but are velocity strengthening. Next, we have the mafic gouges, which are slightly stronger and range from mildly velocity weakening to velocity strengthening as well. Then in the deeper units, we have the cataclastic units that host the pseudotachylite veins. And these are stronger with friction coefficients ranging from around 0.4 to 0.8. And these show more velocity weakening behavior. So a lot of these data points are falling below the 0 line. So A minus B is negative, and we have stronger velocity weakening behavior. But the main regimes that are described by these experiments are that the fault rocks at temperatures less than 150 degrees are velocity strengthening and stable. Between 150 and 400 degrees C, they are more velocity weakening and frictionally unstable. And then again, above 400 degrees C, they transition back to being velocity strengthening and frictionally stable. So let's revisit our geodetic locking models now that we have all of these observations of different styles of slip behavior on the Mayu Fault. So remember, model 1 was shallow locking with creep at all depths below about 2 kilometers. And model 2 had shallow interseismic creep above a more strongly locked zone at depth, transitioning back to a seismic creep below that locked region. So slip behavior, we have Holocene earthquakes up to magnitude 7.3 based on the coral reefs uplifted on the footwall of the Mayu Fault. We see paleoseismic slip at 10 to 12 kilometers depth as evidenced by pseudotachyllites and their ages. We see mixed frictional viscous slip in the cataclastic units as evidenced by mutually cross-cutting brittle and ductile microstructures. We infer creep from about 15 to 25 kilometers depth based on the microseismicity, which represents small frictional failure within a predominantly creeping myelinitic shear zone. And finally, we saw the frictional stability transitions from low temperature velocity strengthening stable frictional slip to 150 to 450 degrees C, frictionally unstable velocity weakening slip, and then a transition back to velocity strengthening at temperatures above 400 degrees C from the velocity stepping experiments. All of these inferences of fault slip style and slip behavior point to model 2, which shows deeper locking, which we would expect to be able to generate the larger earthquakes recorded in the corals and the pseudotachylites. Down dip of this, we have the creep in the myelinitic shear zone, and up dip of this, we have stable aseismic frictional creep in the shallowest saponitic gouges. We can compile all of these results together into a summary figure like this. So here's the Damon Dome, and here's the fault surface. So the fault rocks are shown in grayscale. The shallowest part of the fault zone is inferred to be composed of these saponitic clay-rich gouges, which are weak and velocity strengthening. Going deeper, we have the mafic gouges, which transition into the cataclysite units, which host the pseudotachyllite veins. And here we transition from being creeping, geodetically creeping, to geodetic locking. So in red and blue, we have the inferred degree of locking as seen geodetically. And as we transition into the cataclysite units, we see stronger locking, which is transmitted to the surface as a dip in the velocity profile in the coastward velocities. As the fault steepens at depth, we transition back into the myelinitic shear zone, which is predominantly creeping with these small microseismic failures. So some conclusions of our study are that low-angle normal faults are not necessarily aseismic. We found through the rate and state friction modeling that their seismic style depends strongly on both the magnitude and distribution of frictionally unstable velocity weakening fault rocks. Our GPS experiment showed horizontal extension rates of about 8.3 millimeters per year across the Mayu fault, which correspond to dip slip rates of 8 to 11 millimeters per year on the low angle normal fault. We find the shallow frictional creep in the shallowest 5 kilometers of the fault zone, up dip of a more strongly locked zone, which itself is up dip of a creeping myelinitic shear zone, is the most likely model of active slip on the Mayu fault. And finally, we find that low angle normal fault earthquakes could be up to magnitude 7. So these faults cannot be ignored in future seismic hazard assessments. Thanks, and I'll take any questions now.